For 30 years, one of humanity's most powerful telescopes was drowning in its own data, capturing galaxies faster than any human team could ever hope to study them. Then artificial intelligence stepped in, and what took astronomers years to analyze suddenly started taking days. What it found buried inside that flood of information was something nobody expected to see this soon. The James Webb Space Telescope was built to peer deeper into the universe than any instrument before it, catching faint infrared light from galaxies that formed hundreds of millions of years after the Big Bang. But there was always a hidden cost to that power. Every image Webb captures is packed with noise, faint smudges, scattered light, and imperfections that make it incredibly difficult to tell a real distant galaxy apart for years. The only real solution was patience. Astronomers would point Webb at the same patch of sky again and again, stacking dozens or even hundreds of exposures together, slowly averaging out the noise until faint objects finally became visible. And this approach works, but it comes at an enormous cost, eating up some of the most valuable and limited observing time on the most in-demand telescope ever built. That is exactly the problem a team of researchers set out to solve, and the tool they built to solve it is quietly reshaping how astronomy gets done. Instead of relying purely on stacking more and more exposures, they trained an artificial intelligence system to recognize the difference between real cosmic light and random noise, learning patterns that would take a human lifetime to fully catalog by hand. The result is a system that can look at just a handful of short, relatively noisy exposures and reconstruct an image nearly as clean and detailed as one built from more than 20 times as much observing time. In practical terms, that means astronomers can now get results that once required 168 separate exposures using only 8. The telescope effectively became several times more efficient overnight, without a single new piece of hardware ever being launched into space. When the researchers first tested this system on real Webb data, rather than simulations, something remarkable happened. Buried inside images that had already been studied and picked apart by scientists, the AI revealed faint, previously invisible galaxies, some of them dating back to the first 500 million years after the universe began. These were not obvious features that people had simply overlooked. They were signals so faint they had been completely lost in the noise until the AI learned how to pull them out. Before you keep watching, if this kind of real breakthrough in how we explore the universe interests you, go ahead and hit like and subscribe, because there's a lot more of this coming. Naturally, the first question any serious scientist asks about a tool like this is whether it can be trusted. An AI that generates images runs the very real risk of hallucinating, essentially inventing details that look convincing but do not actually exist in the underlying data. If a telescope worth billions of dollars is going to have its data filtered through an algorithm, that algorithm had better not be quietly making things up. To understand why this concern is so serious, it helps to remember just how much is riding on every single image Webb captures. Observing time on this telescope is one of the most valuable resources in modern science, awarded only after fierce competition among proposals from research teams around the world. If an AI system introduced even small systematic errors into that data, it could quietly mislead entire fields of research built on top of those images. To address that concern, the team behind the system ran an extensive series of tests before trusting a single result. They deliberately injected fake signals into real data, then checked whether the AI could correctly identify them without being fooled or missing them entirely. They trained the system on smaller amounts of data than what was actually available, then compared its predictions against the full, high-quality dataset to see how closely they matched. Only after passing round after round of these checks did the researchers trust the system's output enough to search for real, previously undiscovered galaxies. When independent astronomers reviewed the results using deeper, fully stacked images taken separately, the vast majority of the objects the AI had revealed turned out to be genuine, confirming that this was not a case of an algorithm inventing structure where none existed. The technical name for this system comes from the way it was designed, built specifically to strip noise away from short exposure images while preserving every faint, genuine detail hidden underneath. Rather than simply blurring or smoothing an image the way older noise reduction tools often did, it was trained on massive amounts of real, astronomical data, learning the subtle statistical difference between the shape of true starlight and the random static. That what makes this breakthrough so significant is not just the discovery of a few extra galaxies, it is the sheer amount of observing time this technology effectively creates out of thin air. Every hour of Webb's schedule is fiercely competed for by scientists around the world, with proposals for observing time vastly outnumbering the hours actually available. A tool that can extract 20 times more information from the same amount of telescope time is, in a very real sense, like building several additional space telescopes without spending a single extra dollar on hardware. Some of the heavy computational lifting behind this shift is being handled by powerful graphics, processing hardware originally designed for entirely different industries. The same style of high-performance computing chips that power video games and modern artificial intelligence systems are now being repurposed to chew through terabytes of raw telescope data, turning what used to be a years-long analysis process into something that can be completed in a matter of days. This kind of AI-powered image reconstruction is part of a much larger shift happening across astronomy right now. Just a few years ago, when Webb's very first images were being prepared for release, teams of researchers were already building machine learning models designed to automatically detect and classify galaxies buried inside the telescope's data, rather than relying purely on humans scanning image after image by eye. Since then, that early groundwork has evolved into something far more powerful. Machine learning systems are now being used to identify subtle patterns in exoplanet atmospheres, to spot rare and unusual objects hiding in massive surveys, and to sharpen and clean images in ways that would have been considered nearly impossible only a decade ago. Webb generates such an overwhelming volume of data that human researchers alone could never hope to fully explore all of it in a reasonable amount of time. The scientists working on this specific noise reduction system say their approach is not meant to replace traditional observing methods, but to work alongside them, squeezing far more value out of every single exposure Webb takes. Rather than choosing between capturing new targets or spending more time perfecting old ones, astronomers may increasingly be able to do both at once, letting AI extract hidden detail from data that would otherwise be considered too noisy to use. And this technology is not stopping at James Webb. The same underlying approach is already being adapted for use with the newly operational Vera-Rubin Observatory, a massive ground-based telescope built in the mountains of Chile. Unlike Webb, Rubin sits under Earth's turbulent atmosphere, which naturally blurs incoming starlight before it ever reaches the telescope's mirror. Rubin was designed from the start to scan the capturing a kind of ultra-high resolution time-lapse of the universe stretched across an entire decade. Its mirror alone stretches more than 27 feet across, built at a cost of roughly $800 million, a fraction of what space-based telescopes like Webb cost to design, launch, and operate. By applying similar AI-driven noise reduction and sharpening techniques, researchers hope to make Rubin's ground-based images approach the clarity of images taken from space, effectively fighting against the atmosphere itself, using nothing but clever algorithms. If this works as well as early results suggest, it could dramatically boost the scientific value of one of the most ambitious sky surveys ever attempted. Researchers involved in this work have pointed out that the real value of this technology is not measured only in the number of new galaxies it reveals, but in how much return the public gets on an enormous shared investment. Telescopes like Webb and observatories like Rubin were built using billions of dollars in public funding, and every extra ounce of scientific value squeezed out of that hardware benefits the entire research community, not just a single team or a single discovery. This entire story is a reminder that some of the most important breakthroughs in space exploration are not always about launching bigger, more expensive hardware into orbit. Sometimes the biggest leap forward comes from learning how to listen more carefully to instruments we already have, extracting signals that were there all along but hidden just beyond the edge of what human eyes and traditional methods could detect. There is something genuinely poetic about it too. Light from some of these newly revealed galaxies has been traveling toward us for over 13 billion years, quietly waiting in Webb's raw data for the right tool to finally set it free. It took an artificial intelligence system trained by researchers on the other side of the planet from where that light first began its journey to finally let humanity see it clearly. It is worth pausing on just how strange that timeline really is. These galaxies formed when the universe itself was still in its infancy, barely a few 100 million years removed from the Big Bang. Their light has been crossing the cosmos ever since, arriving at Webb's mirror as one of the faintest signals imaginable, buried under layers of noise that no human eye could ever hope to untangle unaided. For decades, the standard solution to that problem was simply more time, pointing a telescope at the same patch of sky for longer and longer stretches, hoping the faint signal would eventually rise above the noise. That approach works, but it is slow, expensive, and fundamentally limited by how much observing time any single telescope actually has available in a given year. What this new approach demonstrates is a fundamentally different way of solving this same problem. Instead of brute forcing a cleaner image through sheer observing time, the AI learned the underlying statistical signature of real astronomical signals well enough to separate them from noise using far less raw data than traditional methods would ever require. Scientists involved in this research have been careful to emphasize that this is very much the beginning, not the end, of what AI-assisted astronomy can achieve. As more of Webb's archive gets reanalyzed using these techniques, researchers expect to find even more galaxies hiding in plain sight, waiting inside data that has technically been sitting in public archives for years, unseen simply because nobody had the right tool to look closely enough. This idea that entire discoveries might already be sitting quietly in datasets we have had access to for years is one of the more thrilling implications of this whole story. Webb has been collecting data since the middle of 2022, and every single observation it has ever made is eventually stored in public archives, available for any researcher anywhere in the world to study. That means the next major discovery from Webb might not come from a brand new observation at all. It might come from someone quietly reanalyzing old, already published data using a smarter algorithm than the one available when it was first collected, uncovering objects and details that were technically captured years earlier but never actually seen by anyone. And that pattern is likely to repeat again and again in the coming years, as more researchers apply similar tools to the growing mountain of archived space telescope data. It raises a genuinely exciting question for anyone following space discoveries closely. If a single well-trained AI system can quietly double or even multiply the scientific output of a telescope that already cost billions of dollars to build and launch, what might be hiding inside all the other astronomical datasets we already have, still waiting for someone to build the right algorithm to finally reveal it? The broader lesson here extends well beyond astronomy, as instruments across every scientific field continue producing more data than human researchers could ever manually review. Tools like this one are quietly becoming just as important as the telescopes, sensors, and satellites collecting the raw information in the first place. The next great scientific leap may not come from a bigger mirror or a more powerful rocket, but from a smarter way of listening to what we already have. The team behind this specific project was led by researchers at a major university, working alongside collaborators who specialize in extragalactic surveys and deep space imaging. Their work was published in a leading scientific journal, going through the same rigorous peer review process that every major astronomical claim has to survive before it becomes part of the accepted record. That level of scrutiny matters, especially in an era where sensational, unverified claims about AI and space discoveries spread far faster online than the careful, peer-reviewed science actually behind them. This particular breakthrough earned its place in the conversation the hard way, through tested, verified, repeatable results rather than... For now, the story of this discovery is a reminder of something surprisingly simple, wrapped inside some of the most advanced technology humanity has ever built. Sometimes the universe is not hiding from us at all. Sometimes it has been sitting right there in plain sight the entire time, waiting patiently for someone to finally learn how to look closely enough to see it. If you want to keep seeing real breakthroughs like this one explained clearly, without the exaggeration and hype so much of the internet is filled with, make sure you are subscribed. Because the universe keeps getting more detailed every single time we learn to look a little more carefully.